Welcome. Have you ever looked at a statistical report and just your brain starts to hurt a little? You're not sure if you're looking at a plausible range or, a final decision. Trust me, you're not alone. Today, we're going to clear up one of the most fundamental mix-ups in stats, the real difference between confidence intervals and hypothesis tests. Let's get this sorted. Does this sound familiar? Maybe you've heard this from a professor, a colleague, or maybe you've just thought it to yourself. It's such a common hurdle, and that's because these two ideas, hypothesis tests and confidence intervals, they're really closely related. But here's the thing. They are built to do two completely different jobs. And that is the big question, right? That's what we're going to break down right now. By the end of this, you're going to have a super clear toolkit to tell them apart and know exactly when to use each one. Okay, let's start with tool number one, the confidence interval. And look, if you only remember one thing about it, let it be this. Its entire job is estimation. That's it. It is not here to make a final yes or no call on some theory. So what is it really? Well, I like to think of it as a statistical fishing net. We take a sample from this huge population, that's the ocean, and from that one sample we weave a net. That net is our range of values, and we're pretty confident that the true value we're after, say the true average weight of all fish in the ocean, is caught somewhere inside that net. So what does this 95% number actually mean? Now, this is a classic trip-up. It's not the probability that the one interval you just calculated has the true value inside it. Instead, think of it as a long-run capture rate. It's about the method. If we were to cast our statistical net 100 different times, we'd expect about 95 of those nets to successfully catch the real value. It's a measure of our method's reliability over time. So, here's the bottom line. A confidence interval gives you a plausible range. It's your best guess, plus or minus a bit. It answers the question, okay, where do we think the true value probably is? It absolutely does not answer, is my theory right or wrong? For that, well, we need a whole different tool. And that brings us to our second tool, the hypothesis test. So if the confidence interval is all about estimating, the hypothesis test is all about deciding. It's designed to help you make a choice between two competing ideas, using your data as the evidence. The logic behind a hypothesis test is actually pretty simple when you break it down. It all starts with an assumption we call the null hypothesis, which is basically the boring, nothing interesting is going on here scenario. We just assume that's true for a second. Then we look at our data and we ask, all right, how weird is this result if we assume nothing's really happening? And this leads us to the heart of the test. If our data shows us something that would be incredibly rare under that nothing's happening assumption, we start to get a little suspicious, right? At some point, the result is so unlikely, we're kind of forced to say, you know what, maybe our starting assumption was just wrong. This is exactly where the famous and often misunderstood p-value comes in. All the p-value is a number that measures that weirdness we were just talking about. It answers this one specific question. If nothing interesting is truly going on, what's the probability we'd see a result at least as extreme as the one we got? So a tiny p-value means our result is super surprising, and that's powerful evidence against our initial nothing's happening idea. But wait, the p-value doesn't get to make the final call all on its own. It's just the evidence. That evidence needs to be compared against a standard, a rule that we set before we even look at the data. This is the big showdown, evidence versus the standard. So let's put them side by side. The p-value is the evidence you calculate from your specific data. It can change every time you take a new sample. Alpha, on the other hand, is the rule. It's the strictness of your test. It's the line in the sand you draw beforehand to decide what's going to count as unlikely enough to be significant. So this alpha, which you'll almost always see set at something like 0.05, is your significance level. Think of it as the amount of risk you're willing to take of making a very specific mistake. Basically crying wolf. In stats, we call this a type 1 error. It's when you reject the nothing's happening idea when, whoops, it was actually true. An alpha of 5% just means you're okay with having a 5% chance of making that kind of mistake. And here it is, the big finish. The whole thing boils down to this one simple, powerful rule. You compare your evidence, your p-value, to the standard you already set, your alpha. And if that p-value is smaller, it means your result is rarer than your own cutoff for what you decided was rare. And so, you reject the null hypothesis. The evidence is officially strong enough. Now, you might see one other term floating around, the critical value. Don't let it throw you off. It's just another way of thinking about your alpha level. Instead of a probability, the critical value is the actual point on the graph that marks the boundary. If your test result falls past that line into what's called the rejection region, you do the exact same thing. You reject the null. Okay, wow. We've looked at all the different pieces of the puzzle. So let's put it all together now into one clear, simple toolkit so you can walk away from this knowing exactly what each part does. All right, think of this as your new cheat sheet. The confidence interval, its job is estimation. It asks, what's the likely range for the true value? Alpha, that's your decision rule. It asks, how strict are we going to be? The p-value, that's your evidence. It asks, just how unusual is our result? And finally, the critical value, that's the boundary. It asks, where exactly does the reject zone begin? See, two totally different toolkits for two very different jobs. So, what does this all mean for you in the real world? It means you now have a much sharper lens to look at data. The next time you see a news headline or some new study, you can ask the right question. Are they just estimating a value with a range, or are they testing a specific claim to make a hard decision? Just knowing that difference makes you a way more critical, way more savvy consumer of information. So, what's the first claim you're going to go investigate?